Hi, everyone. Thanks for joining us here today. My name is Toby, and I'm here with Babneet. And today we're going to talk to you about the future of native libraries in the Java world. So next slide. So here are some necessary disclaimers. You can move on. Next. So a bit about us. Babneet and I are developers on the OpenJ9 runtime team. We're based in Ottawa, Canada, and we work on the OpenJ9 JVM. So OpenJ9 is an independent open source implementation of the Java VM. It's known for small footprint and fast startup, which is good for cloud applications. But today, next slide, we're here to talk about native interop and how it works today. And we're also going to discuss what are some of the problems with the current solution for native interop and how Project Panama solves these. So next. So by native interop, what I mean is interacting with native libraries in Java code. So you're writing an application, there's a native library that does something that you like, and you want to interact with it using Java code. So a lot of the use cases today are off CPU processing, so things like CUDA and OpenGL. Also machine learning, there are lots of machine learning libraries out there like TensorFlow and crypto libraries like OpenSSL and linear algebra libraries, and many others that Java developers want to use in their Java applications. So next slide. So the current solution for native interop today is, the main one is JNI, Java Native Interface. And this is often used in conjunction with ByteBuffers and SunMist. And so we're going to take a look at an example next to see how this works. So here's basically the overview of interacting with native libraries. First, you write Java code, and you write your native function declarations, and then you generate the Java class files using Java-C. And then you have to write the native header function declarations, or you can use Java-H in some older JDKs where it's still available to generate the header files. And then you have to write the native method wrappers, and then you have to compile that, put it into a library, and then you have to load the library. And then at runtime, the JVM links with your handwritten library, which then calls the actual native libraries that you're interested in. So we'll walk through this step by step just to get a better understanding. So next slide. So here is an example. This is a native application. It's just plain C code. It uses a native library called libcairo, and libcairo is just a graphics library. So in this small example, what's going to happen is it's going to create a box that simply prints out hello world. So if you go to the next slide, you can see there's the output in the bottom right. So there are a few native functions here. There's about 10 native functions that are called here. So it's a very simple example. So in the next slide, we're going to try to do the same thing in Java code. So as previously mentioned, the first step is to write the native function declarations. So for every native function that you want to call, you have to provide a declaration, as you see here. So these are all the native functions that were used in the example. The one thing you'll notice is that because in Java, there's no way of representing native types, we kind of have to use longs to represent pointers. So this is one of the drawbacks, as you're essentially losing type information. And if you have a very complex code, that type information, it can be very important in understanding what you're doing, and not having it can lead to bugs. So after you've written the native function declarations, next, then you have to write the code that will call it. So this code looks a lot like the example where we're calling the native functions, the native declared functions in Java. And as you can see, we're using longs instead of the actual types. And it's not shown here, but for the macro definitions, we had to define them ourselves because in Java code, you can't import the native header files that defines them. So you have to define all the macros yourself, which is another burden for the developer. But once you've done all of that, you essentially write the application as you would in the native C case, and then you compile this. So next. So what we saw up until this point was all the stuff you do in Java code. When you're using JNI, you still have to do a lot of work in the native layer. So you have to define the native header declarations for all the native functions that you're using in Java. So this is, Java H can generate this for you, or you can handwrite it yourself. So for every native function, you have to specify, the package, class, and then function name. And you do this for each function that you're going to call. Next. And then you actually have to provide the implementation. So the way JNI works is you call into a wrapper function, which then calls the actual native function. So as you can see, the function that we actually want to call in this case is the Cairo create, but we have to provide a wrapper that is called from the JVM to which calls the actual native function. So for every native function you want to use, you have to provide a wrapper function for each one. And if you're going to use a lot of native functions in your application, this is a very big overhead because you have to provide a native wrapper for each one. In the second function in this case, you'll see that we want to provide a string. So another issue is that Java strings and native strings are not the same. So in this case, we actually have to copy the buffer, which contains the characters, into a native buffer. This is done with the getString UTF-chars of JVM callback. And so this copies the strings from the Java heap onto a native heap, and then we can pass the native version of the string to the native function. And then after that, we release the memory. So this marshalling cost also introduces an overhead. It's a performance overhead because you have to call in and then copy the array. So this is something that ideally you wouldn't want to do a lot of because it can make your application slower. So next. So to summarize, some of the drawbacks of JNI are that as a Java developer, you have to know C or C++. Essentially, you have to write native code in order to use JNI. And there's lots of code you have to write. You have to write native wrapper for every function that you want to use. There are also issues with type information. And Java cannot represent native types, and so you often have to use a type that like longs that can kind of encapsulate pointers, but you're losing type information, which can lead to bugs. And for things like strings or even just arrays on the Java heap, if you want to use them in native code, you often have to copy the data in order to use them natively. And so this marshalling cost adds an overhead. There are some techniques that people use to avoid this. Some people use Unsafe, Sunmisk Unsafe, or JK internal Misk Unsafe, or direct byte buffers. So instead of using instead of marshalling and non-marshalling off the heap, you can just allocate the memory off heap directly. And so this is another solution. But another problem is that it's slow. The transitions from Java to native is slow because you're essentially calling a wrapper function before you call the native function. So there's an indirection there. Next slide. So as I mentioned, Unsafe is one of the tools people use to avoid the marshalling costs, as it allows you to allocate memory off heap directly. So unsafe is very fast because the JIT basically intrinsifies unsafe operations. So it's lowered down to actual machine instructions. But like with any other pointer-based programming model, it's a difficult model to use. It's very susceptible to crashing, as it's easy to make a mistake and try to dereference inaccessible memory, and this can pose security concerns. So Sun Misconsafe is a restricted API, but there is a more supported one, a JDK internal misconsafe that users can use. So next slide. So ByteBuffer is essentially a safer form of unsafe. So ByteBuffer allows you to, direct byte buffers allow you to allocate memory off heap, and but they also provide bounce checking. So they add a layer of safety. The performance of direct byte buffers is not as good as unsafe, but you do get the safety. So there's a bit of a trade-off there. Byte buffers have limited addressing, so they're limited to 2 gigs because they use an int indexing scheme. And another drawback is that it has non-deterministic memory management, as it relies upon finalization to free the memory. And finalization is a technique that's tied to the garbage collector. The GC essentially determines when it's safe to free. So these are, this summarizes the landscape right now for interoperating with native libraries and some of the drawbacks with the current solutions. Bhavneet's now going to describe Project Panama and how it solves some of these problems.
Thank you, Toby. So now we're going to dive into Project Panama. The goal of Project Panama is to enhance interoperability between the Java code and native libraries, which simply means that we want to make it easier for Java developers to consume native libraries written in C and C++. So there are 3 main components of Project Panama, which will allow us to replace JNI, Unsafe, and ByteBuffer are 2 APIs, the Foreign Memory Access Support API and the Foreign Function Support API. And the 3rd component is a tool named jextract. We will briefly look into all 3 components through some examples. And let's begin with the first component, which is the Foreign Memory Access Support API. It allows access to all kinds of foreign memory, whether it is on heap or off heap. And this covers the property of generality. Further, the API is safe, which means that the JVM won't crash while accessing memory. This is in contrast to unsafe, which can crash the JVM. And the 3rd property is being deterministic, which simply means that the API won't depend on the garbage collector for allocations and deallocations. And this is in contrast to the ByteBuffer, which relies upon the GC garbage collector for cleaning up memory. So let's look at the 3 main abstractions which are introduced in this API. So the first abstraction is MemorySegment, which is similar to a chunk of memory that is returned by malloc in C. And the second abstraction is a MemoryAddress, which is a C pointer. And the 3rd abstraction is a memory layout, which is used to represent C data structures. The cool thing about this API is that it has a good inbuilt error management system. For instance, accessing memory outside the spatial bounds, which is the start and end addresses, will lead to an exception. Similarly, accessing memory outside the temporal bounds, such as a predefined tribe scope, will also lead to an exception. So let us look at some of the examples of using these abstractions. So this is an example of using the MemorySegment abstraction. It has, so in this example, the static method named allocateNative is being used, which allocates memory off the heap. And the memory which is being allocated is of 100 bytes. So the thing to note over here is the try block. It introduces safety by enforcing temporal bounds, which means that the memory is automatically going to be freed as the code escapes the scope of the try block. It also implements safety features for spatial bounds. For instance, if memory is accessed outside the try block, then it will throw an exception, or if the memory outside the start and end addresses is accessed, then it will also throw an exception. Here is another example of memory segment, but here we are using the acquire method, which enforces synchronization. This can be used in a multi-threaded scenario where there are multiple threads trying to acquire the memory segment, and we only want one thread to access the memory segment at a time. So when the acquire is called, one thread needs to leave the try block before another thread can access the memory segment. The cool thing about memory segment is that it can be divided into smaller memory segments through the API, and then multiple threads can simultaneously work on smaller memory segments, which are derived from the larger one. And this covers the memory segment abstraction. Let's move to the next abstraction, which is MemoryAddress, which is simply a C pointer. And in this example, we are extending the previous example of the memory segment. And we are deriving a memory address, which is derived through two methods, base address and add offset. And combination of these two methods will allow us to derive a memory address for any byte in memory segment. So this is simple pointer arithmetic that we are currently able to do in C program, but this is in Java. And so this covers the memory address abstraction. And now let's move on to the last abstraction for the foreign memory access API, which is a memory layout. So the purpose of memory layout is to define the structure of data in the memory segment. So here I've shown a C structure, which is a 10-element array, and it contains two integers, ID and val. And at the end, I've shown how this array will look in memory. So let's look at how to use memory layout in order to access the elements of the array in memory. So in this code snippet, we are defining the struct with the two integers ID and val. The struct is defined through the offStruct method, which is a static method in the memory layout class. And at the end, we get an instance of group layout, which is a derived class of memory layout, and it represents the struct datum, which was seen in the previous slide. And the next step is to define the 10-element array. And to define an array, the memory layout class has a static method named offSequence. And offSequence returns an instance of sequence layout, which is, again, a derived class of memory layout. Here we are creating a sequence of 10 elements of the data layout group layout, which was derived in the previous slide. So the sequence layout instance represents the 10-element array, which was shown 2 slides ago, and which is also shown at the bottom of the slide. So using the combination of offStruct, offSequence, and other methods in memory layout, we can define how data is structured in memory. So once we have defined how data is represented in memory, the last step is to access that data in memory. And this is done through var handles. For those who don't know what a var handle is, in short, it is a type reference to a variable, and it provides an interface to read or write the variable it represents. So in this example, we are accessing data in memory, which through the memory layout instance. First, we get the var handle from the memory layout instance. And in this example, the var handle provides access to all the ID fields in the 10-element array. Then the example depicts the get and set operations using the var handle, which read and write to the memory respectively. So this way, var handles can be retrieved from the memory layout instances in order to read or modify structured data in memory. And this is very simple to operations we can currently do in C. And with this, I think we have briefly looked into the functionality of the foreign memory access API and some of its main components. More details and documentation of this API can be found at the link shown in this slide. And now we move forward to the second API, which is the foreign function support API. The main function of this API is to allow invocation of native functions from Java code and vice versa. And to achieve this goal, it introduces a new type of method handle named native method handles, which target a native function. And a method handle is similar to a var handle. Instead of a variable, it targets a method and it allows invocation of a method. And moving back to the API, we're going to look into the four main mechanisms of this API. The first is how to look up symbols in native libraries. The second is how to call native functions from Java code. Third is how to call Java methods from native functions. And the fourth is how to handle C functions with variable arguments. So the first component of the foreign function support API is to look up symbols in native libraries. To achieve this, a new class named library lookup is introduced. And the process is very simple. We create an instance of library lookup, which loads up the symbols from the library. And then we call the lookup method with the name of the symbol to query it. And then at the end, we get the symbol as a return value. The cool thing of note here is that there are three different approaches to load symbols from a native library. The off default method can be used to access symbols which are already loaded by the VM. The off path method can be used to access symbols provided the absolute path for the library. And the off library method can be used to access symbols of a library given its name. So this summarizes the process of looking up symbols in native libraries. And the next step is to represent and describe native functions and Java methods. The foreign function support API needs to be informed about the return type and input arguments types to the native function and Java methods. This is important to translate the return type and input arguments when passing them between native functions and Java methods. In this example, I've shown a native function sterling, which simply determines the length of a string. And for describing a native function through this API, the function descriptor class is available, which accepts the return type and the input argument to the native function. And for describing the Java methods, we already have an existing class named MethodType in the Java lang invoke package. So this information is used by this API to call native functions from Java code and vice versa. Now we look into the core component of this API, which is the CLinker. And in this example, I've shown the CLinker's ability to perform a downcall, which simply refers to invoking native functions from Java code. First, a method handle is created through the downcall handle method, which is available in the CLinker class. This method accepts a library lookup symbol, a method type instance, and a function descriptor instance, which we covered in the previous two slides. And then the method returns a method handle, specifically a native method handle, which will invoke the native function. And finally, we just need to call invoke on the method handle in order to execute the native function from Java code. So this is how downcalls will be performed through this API, which is simply 2 lines of code. In comparison to JNI, where you had to write all the wrappers, compile the wrappers, and maintain them over a long period of time. Now let's look at upcalls, which is the opposite of downcalls, where Java methods will be invoked from native code. And for this, the CLinker class has a method named Upcalls, which accepts a method handle that will invoke the Java code. And it also accepts the function descriptor for generating a native wrapper. And the return type is going to be a memory segment, which is going to be the address to the native wrapper that will invoke the Java method from the C code. and the memory segment needs to be forwarded to C code, where it will be invoked with the appropriate input arguments. The forwarding is done through a down call, which we had seen in the previous slide. And the native wrapper, which is going to be generated by the Upcalls stub, will set up the stack, registers, and other environment dependencies, such as transitioning from native to VM, attaching to a Java thread, and then invoke will be called on the method handle, which was passed as an input argument to the Upcalls stub method, which will execute the target Java code in the C code. So this is a brief summary of how Upcalls will work in this API. And the final functionality is how variable arguments are handled by this API. So native functions with variable arguments can accept any number of arguments. And to support variable arguments, this example highlights two new types in order to handle variable arguments during generation of a down call handle. And here we should look at the usage of VA list class and the CVA list type. So when the method handle is invoked, a VA list instance needs to be provided with details about the variable arguments list. So here there is an extra overhead of creating a VA list instance before the down call. But this approach is good because it allows us to reuse the down call method handle. And also the VA list instance can be reused with other down call method handles, or it can also be reused with upcall handles. And with this, I think we have briefly looked at the functionality of the foreign function support API and 4 of its primary mechanisms. For more details and documentation for this API can be found at the link shown in this slide. So we just covered 2 APIs, which will be the foundation for the jextract tool to automate and replace the JNI workflow. The API for foreign memory access aims to provide a safe and efficient access to memory on heap and off heap. The API for the foreign function support provides functionality to invoke native functions, which are written in C, C++. And the overall goal here is to provide a new interface which is complete, safe, and performant than the existing alternatives, such as Unsafe, ByteBuffer, and JNI. And so let's look at how will the JNI Panama and Panama workflows differ. So in JNI, we have to write, maintain, and build JNI wrappers to consume native libraries. This is time-consuming, expensive, and requires a lot of human resources. Further, JNI has its performance deficiencies. This makes it very non-ideal and unattractive. On the other hand, the Panama workflow gets rid of the weaknesses of the JNI workflow. Jextract generates a ready-to-use jar file with the required API interface to consume the native library. So we no longer have to write, maintain, or build JNI wrappers. So first thing a user needs to worry about in the Panama world is how to run jextract. So here we can see the working of jextract in the context of the earlier libcairo example, which was covered by Toby. In order to generate the API for invoking the native libcairo functions, we just need to invoke the jextract executable with the required input parameters. So the jextract command line is shown in the slide. The 3 main arguments are the native library name, the package name for the API, which will be generated by jextract, and the header file, which contains all the stubs for the native functions in the native library. After we run jextract, we want to know what is generated by jextract. Here we can see the 5 Java source files generated by jextract for the interface to consume the native Cairo library. These source files are generally available in a jar file ready to be used by a Java application. And so to summarize, once the jar file is generated by jextract, we can directly consume the native library in any Java application. So here we no longer have to worry about JNI wrappers, compile code, generate any libraries, or do any maintenance stuff that we needed to do in the JNI world. So let's look at the internals of some of the classes that are generated by jextract. So here we can look at the cairo_h class, which a Java developer would need to import in order to invoke the native Cairo functions. And a few things to note here. First, these functions are static, so they can be invoked from anywhere. And second, all this code and the required dependencies are generated by jextract. Third, the static functions in this class is what will replace the JNI wrappers that Toby had shown at the start of the presentation. These wrappers are no longer native wrappers. They are completely written in Java and supported using the foreign memory access and the foreign function support APIs, which we saw earlier. And here we can see the libcairo example transformed into using the jar file generated by jextract. Most of the differences are underlined. First, we have imported the cairo_h class. It has the static functions to invoke the C functions and macros from the native Cairo library. And the other thing to note here is that the native functions cannot directly work with a Java string. So the foreign function support API provides a method named toString, which converts a Java string to a C string. And everything else stays the same as seen in the JNI example covered by Toby. So the final step here is to compile and run the Java code with the jar file generated by jextract. So now we have briefly looked at the working of jextract and a simple example. More examples and documentation for jextract can be found at the link shown in the slide. So to conclude, I would like to reiterate that the future for native libraries in the Java world is very promising. It is going to be quicker and easier to consume native libraries with a safer and performant infrastructure.
So I'll just repeat some of the questions raised in the chat. The first question was, in which version of Java will these features be included? So this will first be released as an incubator feature, possibly in JDK 16, but if not, most certainly in JDK 17. And the next question was, what platforms will it work on? When it's fully released, it'll work on all platforms where the JVM is supported. I believe the early access version currently works on Linux and Windows x86. So there's a question about loading a 32-bit library with a 64-bit JRE. Not certain, unless you are about me, what the actual behavior is here. I suspect this will probably trigger an exception due to mismatching reference sizes. I think this would be a similar scenario as trying to load a 32-bit JNI library with a 64-bit JRE today, which I don't believe works. So question, is it planned to have both JNI and Panama? Yeah, so JNI is not going away. JNI will always be there, but Panama is just going to offer basically a better solution. So you will not have to migrate to Panama, but if you decide to do so, you'll have that option. So question, how does this compare to GraalVM and native images? Well, so it's GraalVM, the native image gen is, maybe I don't fully understand the question, but the GraalVM attempts to do something else. It's essentially doing a form of static compilation of your native application. So it's taking your entire application and then compiling it and generating a native binary. Whereas with Panama, you're running a full JVM, but you're able to interact with native libraries more easily. Perhaps maybe you can qualify the question a bit more, but they're really solving two different problems here. Thanks everyone for coming to see our presentation. I hope you guys enjoyed it and learned something new.